Now that we've talked about ethane and how to represent it using a Newman projection and its energies that it can go through during different conformation, let's talk about larger alkanes. So looking at propane here, how do we represent it using a Newman projection? Well, you can see the propane molecule at the top. Here's carbon 1, 2, and 3. Now, the best way to analyze the orientation along a carbon-carbon bond, like we said, is using this Newman projection. So the first thing you need to do is decide where your perspective is in the molecule. So you need to decide which carbon-carbon bond you're looking down. When you have any molecule that's longer than 2 carbons, we have to pick the carbon-carbon bond. Now this is the opposite case when you're going from a Newman projection back towards a molecule. You of course have to think about the fact that this is only one carbon-carbon bond that we're looking down. Anything else attached to it will be shown on the side. Okay, so in our drawing of propane, we're going to choose to look down this C1-C2 bond. So we're going to use this bond as the overlap bond in the Newman projection. Everything else is going to be thought of as a substituent off of those bonds. And you can see that in the GIF here. Here's us showing the rotation from the side view. Here's the side view. And then we're going to look down the carbon-carbon bond, carbon 1, carbon 2. And you'll see that that last methyl group, we're going to write it as a CH3 group and show it as just a group off of the back of the second carbon. So remember, ultimately, Newman projections is just a perspective drawing. We're just changing the perspective of a molecule. And when you're drawing it, you have to specify which bond we're looking along. Because even in something simple like propane, there's 4 different ways we can look along the carbon-carbon bond, and therefore 4 different Newman projections just for this one. So you can see here, if we look down the carbon-carbon bond here, 1, 2, that would be this molecule here. Notice the front has hydrogens, hydrogen, hydrogen, hydrogen. We look down the 1, 2 bond, and this back carbon, CH3 methyl group, is here. Now this is in a eclipsed position in which everything is overlapping. Now we can also look down the carbon 3, 2 position, so going from here to here. And in this position here, we can see, similar to our 1, 2, we have our hydrogens in the front, methyl group in the back, but from this position in which it is drawn, you can see that it is a staggered position. And that's because of where this hydrogen is in respect to this methyl group here. Similarly, we can look down the carbon 2, 1 bond. So that's going from here to here, looking down this way. In this case, because our front is our C2 group, notice that the methyl group is drawn on the front position of the Newman projection. And that's the same if we look down the 2, 3 bond, where the 2 is in the front. Our methyl group would be in the front of the Newman projection. So again, 4 different ways of looking at it. The same molecule, this is the same molecule in all cases, it's just which bond we're looking at using the Newman projection. So let's do a test of this. Let's think about going from Newman projections to drawing and the relationship of molecules in this case. So here we have two Newman representations. And the question is, what is the relationship between them? Are they an identical molecule? Are they constitutional isomers? Remember, constitutional means that they have a change in the bonds, right? You actually have to move a bond. Are they different conformations of the same compound? So that would be a conformational isomer. That means it's just been rotated, but it's the same molecule. Or are they stereoisomers? So here, if we look at this Newman projection, let's think about what this means. Remember that if we're looking down the center here, if we want to turn it to the side, that means that there is a carbon-carbon bond. This front carbon has a chlorine and two hydrogens. So I could write that if I turn this to the side, my chlorine would be at the top. And I would have a hydrogen coming out at me and another hydrogen going back into the page. Right, so this is the front-on molecule turned to the side. Now if I draw these ones on the back carbon, again, our chlorine this time is pointing down in this representation. And then we have a hydrogen coming out at us and a hydrogen going back into the page. So that is this molecule. Now let's draw this molecule. Again, we know that there is a carbon-carbon bond, and I'm just turning this to the side. So the chlorine on this front carbon would be here. And then again, we have a hydrogen coming out at us and a hydrogen going back away. That's this hydrogen and this hydrogen. Now here, we have a hydrogen pointing down on the back and a chlorine coming out at us and the other hydrogen pointing in the back. Now first, let's talk about if these are identical or constitutional isomers. So obviously, just looking at the Newman projection, they're not identical because these are not in identical positions. Are they constitutional isomers? Have we changed the bond position of any molecules? Now I implore you to draw these out. This one might seem a bit simple because it's only one carbon-carbon bond, but when you work with larger molecules, drawing them out from the Newman projection to a normal bond line drawing will help you to see if you've had any movement of bonds. Now what you can see here is that on each carbon there's a chlorine and two hydrogens, and that's the same between both of these, between molecule 1 and molecule 2. This is molecule 2. This is molecule number 1. Right, so we have a chlorine on each carbon and two hydrogens on each carbon. So no change of bonds between the two of them. What you can see instead is that this is just a rotation. Now it's probably pretty simple to view it as a rotation using the Newman projection, because if you looked at this in the beginning, you probably noticed that all of the lines to hydrogens and chlorines were the same, except that this chlorine was rotated from the back in a counterclockwise way. So if we rotate this chlorine here to this position here, you can see that these structures remain the same except for just a rotation of the back. So this is an instance where you have the same different conformations of the same compound, just a rotational conformation. Okay, so let's try a different one. Here we're looking at, again, the same type of question, relationship between Newman representations shown. So in this case, I want you to think about where things are connected and if you can rotate the molecule to get a different conformation. So yet again, we know if we just look at them very simply, they're not identical because the Newman projections are not the same. So they could be constitutional isomers or they could be a rotation. So I implore you to think about if we can rotate this molecule to equal this molecule. So for example, this CH3 group, can it be rotated in a way to be put where this CH3 group is? Now, the answer here is no, it can't. And one of the quick reasons I could tell you is that if you look at this molecule, remember that this front carbon is attached to this hydrogen, and this hydrogen. And the back carbon is attached to this methyl group, this OH group, and this hydrogen. But in this molecule here, we can see that the front carbon is attached to a methyl group, a hydrogen, and a hydrogen. So already we have different attachments. That means there's been a change in a bond, right? We haven't just simply rotated anything around. This actually has a different connection type. So in this case, we actually have constitutional isomers. Now that we've talked about going between Newman projections and the representative side-on views or bond line view, let's talk more about why those eclipse versus staggered conformations are important. Why do we care about them? When we analyzed the conformations of ethane, we saw that the eclipsed conformation was about 3 kilocals per mole higher in energy than the staggered conformation. Remember, that was for ethane, that was just with simple hydrogens, but we saw that when those hydrogens were lined up, it was a higher energy molecule, it was a less stable molecule than when they are staggered. Now, mathematically, what that means is that each of those hydrogens eclipsing is about 1 kilocal per mole. Remember, we have a total of 3 kilocals per mole. So each of these in total is 3 kilocals per mole. So that means it costs us about 1 kilocal per mole of strain per hydrogen overlapping with a hydrogen. Now, what if you look at propane? Propane is larger. There's an additional methyl group on it, as we showed. Now, if you have a eclipsed version of propane, instead you have a methyl group that is repulsing with a hydrogen group. The methyl group is bigger than the hydrogen, so we'd expect that this repulsion interaction would actually be much larger. In this case, we know that the rotational barrier for propane is measured at a total of 3.4 kilocals per mole. Again, there's 2 places where we have hydrogens eclipsing each other and they're interacting. And each of those costs about 1 kilocal per mole, as we saw with ethane. So we know that mathematically, when a methyl eclipses a hydrogen like this, we actually get an energy of torsion strain 1.4 kilocals per mole. So now that we're adding more onto these, the strain increases when you are in this eclipsed interaction. So an energy diagram for propane instead of ethane still looks kind of similar to ethane. We see that when it is in an eclipsed position and we have a methyl interacting with a hydrogen, we have this 3.4 kilocal per mole torsional strain. And as soon as you move by 60 degrees into a staggered position, this drops down to 0. It goes up as you move again, because now yet again, a methyl and a hydrogen are eclipsing, and our other hydrogens are eclipsing as well. And it goes down and up like this. So yet again, same shape as the graph as ethane, except our rotational barrier is higher, meaning that for this molecule, it is even less likely that you will find it rotated into the eclipsed position. So again, while this is a freely rotating molecule, it's unlikely or less likely that you will find it eclipsed instead of in its staggered positioning in its low energy rotational conformation. So now let's think about a situation where you have an even larger molecule. With butane, this is C4H10, so we have 4 carbons. And if we look down the central carbons, this is carbons 2 and 3, right here. This is where our Newman projection will be looking down. You see that you can have the extra methyl groups that are on each end. That's this methyl group and this methyl group here. Let's draw this out as a line bond real fast. So here is our butane. Now we're going to look down these 2 carbons. And so carbon 1 here and carbon 4 here are going to be extra groups coming off of the central bond. So that's how you get this Newman projection here. We have our front carbon number 2. It has 2 hydrogens on it. This is carbon number 2. With this hydrogen, and it has a methyl group in the front with it. That's carbon number 1. And the back carbon, carbon number 3, also has 2 hydrogens on it, as shown. And it has a methyl group attached to it, which is carbon number 4. When we look at butane, it can be in 2 distinct staggered conformations. So unlike in our ethane and propane, when butane is staggered, meaning when the hydrogens are not overlapping, you still have 2 unique types of positions. So again, when groups are not overlapping, we can still have a position called a gauche conformation. That's where the 2 methyl groups here are near each other. They're in a 60 degree apart from each other. Or we can have a conformation where they are staggered, where nothing is overlapping, but the methyl groups are now 180 degrees apart from each other, or an anti-conformation. We talked about these prior, the gauche versus anti. This is relating 2 groups, one in which you have a 60 degree versus a 180 degree difference. Now that steric interaction between the 2 methyl groups, when they're 60 degrees apart in a gauche conformation, we call that a gauche interaction. So even though they are not completely overlapping each other, even though they are staggered away from each other, being 60 degrees away from each other, they still have some amount of interaction, versus when they're 180 degrees from each other in an anti-conformation, the CH3 groups do not engage in steric interactions with each other. So they're far apart, they're not sterically inhibiting each other. So the diagram for ethane looks a little bit, or excuse me, for butane looks a little bit different. Its rotational barriers are going to be dependent on where those two methyl groups are. Now that we have two methyl groups, it's going to change a little bit. So when we have a methyl group and a methyl group completely eclipsing each other like this, and the hydrogens completely eclipsing each other as shown, this version is the highest energy conformation. This is the conformation that is least stable and highest energy. And that's because it's where the two methyl groups completely are eclipsing each other and interacting with each other. When you eclipse a methyl and a methyl, that costs about 2.9 kilocalories per mole. And if we add this up, you can see on the diagram, this whole eclipse equals about 5 kilocalories. So we get about 3 from the methyl-methyl interaction and 1 from each of the hydrogen-hydrogen eclipses. So that is a total of about 5. Again, the highest energy. Now, if we move it 60 degrees, we stagger it away from an eclipse, we have this gauche interaction where the methyls are 60 degrees apart. They still have a little bit of strain even though there's not an eclipse going on, even though they're staggered by 60 degrees. And a gauche interaction is going to cost 0.9 kilocalories per mole. So it's not a very high cost, but it is just slightly more than at a low 0 point of interaction. So just this is 0.9. Notice none of our hydrogens are interacting, and so that's all 0. So we have this total barrier cost of 0.9 kilocalories when you move it into a gauche position. Now, if we rotate again, in this case, our methyl groups are 120 degrees from each other. So there's no gauche interaction, but we do have normal eclipse interactions, right? A hydrogen and a hydrogen are eclipsing each other, so that's not good. That costs us 1 kilocal. And a methyl and a hydrogen are interacting with each other here. We saw that in propane as well. This is 1.4 about, and this is also 1.4. So we get realistically about 3.6, which even though calculated out is about 3.8. But you can see this higher energy because of our eclipse happening on each of the points. Now, if we rotate one more time, our methyls are the furthest away from each other as they can be. None of our other hydrogens or methyls are interacting or eclipsed. They're in an anti-position. This is the lowest energy position, the most likely conformation, and it is at 0. And you can see as you rotate around again, you go through the same types of positioning, an eclipse position, a gauche position, and then a totally eclipsed where we have methyls on methyls interacting, again, the highest energy. So what you see here, what you get from the Newman projection is that staggered conformations are still just an energy minimum. The molecules like to stay in a staggered manner where none of the groups are interacting with each other, whether they be a hydrogen or a methyl, as opposed to eclipsed, where they're completely eclipsing each other. However, the anti-conformation, the position in which you have your big groups, in this case it's methyls, your bigger, larger groups completely opposite of each other and staggered, is going to be the lowest in energy. And eclipsing groups, where you have the big groups eclipsing each other completely, is going to be the highest in energy and the most unstable. So generally what we get from this is, as you get bigger and bigger and bigger, it's harder to kind of look at these using Newman projections. But ultimately, conformation analysis of large alkenes shows that positions in which you have all anti-conformation, so conformation where those methyl groups, the big groups, are completely away from each other, are the most stable. And when we look at that from the side, it has a zigzag appearance. And this is actually why we always draw our molecules, why I've been drawing these alkanes using a zigzag appearance. For example, pentane, shown here in its all anti-conformation, is in this zigzag pattern. Hexane, again in the zigzag pattern here. Okay, so let's try out a question now using a new molecule. Let's identify the least stable conformation of one propanol. Now remember, in general, we know that if something is staggered versus eclipsed, eclipsed conformations are always less stable. So I'm going to get rid of our staggered options. This is a staggered option, and this is a staggered option. Here are our eclipsed options. In B, we have an OH group with a hydrogen eclipsing each other, and a methyl and a hydrogen, and a hydrogen and a hydrogen. These are the groups eclipsing each other. Here we have hydrogen, 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 but our OH and our methyl group here are eclipsing each other. Now, you don't need to know anything about these groups as far as functional groups, but you can tell that an OH group is bigger than a hydrogen. And remember that when you have big groups eclipsing each other completely, this is always the least stable conformation. So here where we have our methyl and our OH eclipsing each other, versus even though this is eclipsed with hydrogens, the OH and the methyl group are away from each other. Okay, so let's try another question. Here, instead, select the most stable conformation of butanoic acid. Now, as I just said, remember that eclipsed conformations are unstable, whereas the staggered conformations are more stable. So I'm going to already just get rid of our eclipsed conformation as an option. Here we have all different staggered conformations. We have one in part B where our big group here, our CO2H, and our big methyl group in the back are completely opposite of each other. In part C, we have our CO2H group and our methyl group staggered, but still near each other. And here, this is an interesting one. Our CO2 group, H group, and our methyl group are actually connected on the same carbon. Notice here, they're connected to the carbon in the front, whereas here, the methyl group is connected to the front carbon, but the CO2H group is connected to the back carbon. And here, the methyl group is connected to the back carbon, and the CO2H group is connected to the front carbon. So in this case, when they are separated by a bond, they are already further apart. But even seemingly so, you can see that these two are 120 degrees from each other versus in our completely opposite 180-degree situation. In an anti-situation where the two big groups are completely opposite of each other and staggered, you will see that is the most stable. Okay, and that wraps it up for talking about conformation and Newman projections. I suggest you go through the link that I provided and look in more detail at the videos to kind of get an idea of the spatial relationship of the 3D positioning of molecules and their Newman projections. Also, make sure you understand the energy diagrams and how you can calculate how much strain is occurring rotationally based on the positioning, the rotational positioning of groups along a molecule.